For those of you that don't know the joke, and it's really not much of a joke, the ducks are the mascot of the University of Oregon, which is good because the mascot of Oregon State are the beavers. University of Washington are the huskies. If I had my choice, I wouldn't move. Okay, so much for the spontaneous part of the presentation. What I'd like to do is talk to you about one of my passions. They say I'm going to give a talk tomorrow about my other passion. You know, to be my age and have two passions left, it's not so bad. The talk tomorrow is about underwater volcanoes, which is really the central theme of my life. But this broader issue of the understanding of the planetary life support system is an extremely important thread that I would like many of the folks that are involved in oceanography to work with the public who is interested in oceanography. It's time we wove the threads of all the examinations that go on in oceanography into a tapestry for the future that actually is extremely important because, as I'll try to make the case in my talk, we are all dependent on the ocean. Whether we live near it or not, we are dependent on it. And that is one of the central themes of what I'll talk about. So that's the first point. If those of you who have had your dinner and you need to catch a few winks, I'm good with that. That's why I put this slide in. It's got all the key elements of the talk, so you know, you could be, if you like, I can wake you up about 3 minutes before the talk, and you know, when the lights come on, you'll just look like you've been awake the whole time. And if you master these 4 points, I have nothing else to share. So the oceans are essential to life on the continents, and they are more than just essential. It's the quality of the life that we have on the continents is very much a function of the health of the ocean and the patterns of the ocean and the movement of the ocean and the ecosystems that are involved in the ocean. So that's the area that we're going to head. And part of that has to do with the fact that the oceans are so complicated. They are so incredibly complex, and it's not surprising that they're complex because the oceans have been around for at least 4 billion years, probably longer. Life originated on this planet somewhere, we think, in the vicinity of 3.8 to 4.2, 4.3 billion years ago. So the oceans have, in the physical, chemical, and biological sense, have sort of co-evolved with the evolution of life, with the evolution of the salinity of the ocean, with the evolution of continents that have grown in terms of surface area of the planet throughout geologic time, with the shifting currents and the shifting patterns of circulation of the ocean have changed through the geologic history. About, say, 3.5 billion years ago, the continents, as you know, are about 1/3 of the surface of the planet right now. At that time, they might have been 5%. So it was really a planet ocean in the beginning. And many people believe that life may have originated on Earth. This is controversial, I acknowledge that it's controversial, but the idea that Darwin came up with, that life began in a warm, shallow pond somewhere on the surface of the planet at 3.8 to 4 billion years ago, is probably not true, because it was around 2.2 to 1.8 billion years ago that we began to develop oxygen in the atmosphere, and it took a long time to get to the level of oxygen that we now have. And oxygen is the basic requirement for the protection that we have in the atmosphere. the ozone in the atmosphere protects us from cosmic radiation. So anything that lived in the near surface of the ocean, or of the planet for that matter, in those early years would have been irradiated and probably destroyed. So life probably began in the ocean, maybe deep within the ocean, we don't know. But it is an area of very active research and a lot of interest from the point of view of folks in NASA, because it's very clear that if it takes an ocean to develop life, and maybe volcanoes to develop life on a planet, then there are other bodies in the solar system, literally the moons of Jupiter, and maybe one or two of the moons of Saturn, where such conditions are met. So to some extent, what we're doing by studying the planet oceans that we are so dependent upon, we are also simultaneously doing fundamental research into the early ecology and the evolving ecology of the entire planet. And there are some surprises. I'll share a couple surprises with you with regard to these underwater systems. The complexity of the oceans is almost unbelievable. There are hundreds and hundreds of examples of processes that are all linked to one another. So part of the complexity is that there are many processes that operate in the ocean. But the other side of that complexity is that most of the processes in the ocean interact with one another. So you can imagine a society in which you had, say, 50 people, but none of them talked to one another and none of them interacted with one another. It would be a certain kind of society. But if they all began interacting with one another, all of them, then the complexity of that society is much greater. And in fact, for scientists, we refer to that complexity as, it increases as n factorial, which is, if say n is 6, it would be 6 times 5 times 4 times 3 times 2 times 1. So you can see that very quickly the complexity goes way up. If you have hundreds of processes in the ocean that are all interacting with one another, then it's not surprising that we really have a very hard time understanding this complexity. The other thing is that the oceans are changing very, very, very significantly, and in some cases rapidly. But they're also changing unpredictably. And I'm talking about the global ocean system. I don't get to see you very often. I'll step sideways here. But, and so that's a challenge. And one of the best solutions to that challenge is computational modeling. That is, you have very, very powerful computers, and you use lots of mathematical equations to represent the processes individually, and then you have those processes individually begin interacting with one another in cyberspace, and out the end comes an absolutely exquisite set of models that might look like the global ocean. But the problem is, although computers have grown very rapidly and become much more powerful, the capacity that human beings have of observing processes operating in the oceans is truly in its infancy. And certainly we have not had the ability to examine and document and archive and offer to computational scientists. We have not been able to look at the full complexity of the ocean ever. So those are the thresholds we're at. We can talk about exploration, and many people go around the planet in ships and they talk about taking robots and having the robots go to far-flung places. The period, I want to say this very carefully because I don't want to offend anybody. The period of physical exploration, that is going new places, has been very productive. We've become very, very good at exploring the planet, although we're not very good at mapping the deep ocean floor, partly because the ocean is semi-opaque to electromagnetic radiation, meaning that if you shine a flashlight into the ocean, it won't go very far. Meaning no matter what, if you're down, and I've done this many, many, many times, if you're down about 300 to 400 meters, half a kilometer, there's light, but there's only two sources that are really obvious. One is the bioluminescence of the animals that are out there, and the other is the submarine's lights. But sunlight doesn't go that deep. So most of the work, for instance, that I do is 2 to 2.5, 3 kilometers deep. There's no natural light there. Okay, so light becomes a very, very important parameter in terms of mixing the upper part of the ocean. The sophisticated models that we have can become far more sophisticated if we can come up with ways of offering those models first-class, high-quality, interdisciplinary science in terms of observations and data, and then the models can input that data, and we crank on the model and see whether the model produces what we actually see. If it doesn't, you change the model, and then you do it again. But you constantly have the new data. So, and over decades and decades and decades, we will have improved these models so they can get to the point of predicting what changes might take place in the ocean, which, as you will see later in the talk, is a crucial issue. If the ocean changes dramatically, but unexpectedly, then human beings there will be major impacts on human beings. So sophisticated models need data to become predictive. And then finally, the thing that I have been, in fact, publicly castigated for more than once is the implication that the day will come when we will have to learn to know enough to not just change the way we perceive the oceans and the planet, but to manage the way the oceans function. Right now, humans aren't anywhere close to that. And there's a whole field of study called geoengineering in which it's almost like it's almost imbued with a religious kind of controversy. Some scientists will stoutly say, in no uncertain terms and often accompanied by colorful epithets, they'll say, you can't do that. And others will say, we have to learn how to do it. And so that's where we are right now. I am only introducing this to you not to show you the scars on my intellectual back, but simply to say there's a dialogue going on, and the dialogue involves us, but the dialogue will increasingly involve your children and your grandchildren. What happens on the planet over the next 40 to 50 years is absolutely crucial with regard to the ocean. The ocean is the engine that drives the stability of our planetary ecosystem, and we are an integral part of that. So bear that in mind as I talk, and by all means, if there's a question that you have, I'm told that this lecture is not on a crucial timeline as the earlier one was. So if you have a question and you are itching to ask the question, the chances are others are wondering the same thing. So please speak up. I will warn you, I have a plane on Friday morning. I will have to leave by then, but between now and Friday morning, I don't know how many of your speakers say this, but I'm yours. Okay, so when scientists start down a path to study a system, this is what they do. They say, okay, what is the system? Because modelers like to say, well, what's in the system and what's outside the system? And they like to say, what's the energy input to the system and what's the energy output from the system? So once you define the system, then you are in pretty good shape, at least at the beginning. Well, the system is not the Chesapeake Bay. The system is not North Atlantic. The system is not even all of the Pacific Ocean. It's the whole planet. It's the atmosphere. It's the ocean. It's the continents. And we'll find there's a third element. But this is the system. We are dealing, this is the one we have to model if we expect to understand it. And there's a challenge that we have. The challenge is basically to optimize the benefits and to mitigate the risks of living on a planet that is really driven only by two energy sources, two primary energy sources. The first of those energy sources is solar energy. It's one that you're very familiar with, and because I live in Seattle, I rarely see. But what does solar energy do? Well, look at the clouds on that picture. Think about the rainfall. Think about all sorts of things that solar energy does. It drives the winds, the waves, the tides, the cloud formation, rainfall, storms. Most of all, it's important that it drives photosynthesis, which keeps us in oxygen. And equally important, perhaps, is that the influence of solar energy in terms of cycling carbon through the atmosphere and the oceans is very, very important. We're all made up of carbon. We generate carbon. Since the beginning of the Industrial Revolution, a massive amount of fossil fuel has been converted to CO2, if nothing else. And therein lies the story. We'll come back to the story, but it's a big deal. The other is the one that turns me on, not that I'm not interested in sunshine, but volcanoes, earthquakes, formation of metal deposits, the movement of continents, literally the movement of continents, and I might add, it's a framework for metal deposits and for energy deposits, but it also is a source of the alternative to photosynthesis. Photosynthesis, you all know something about. You no doubt have photosynthesis is going on in your own backyard, I bet. But do you have access to chemosynthesis? Maybe, maybe not. If you have any really dark black muds in the bottom of the pond in the back acre there at your house, you might have a little bit of chemosynthetic activity. But chemosynthesis is something that has become very fascinating in the past 30 to 40 years because we have discovered on the seafloor that underwater volcanoes spew vast amounts of extraordinarily high temperature fluids, which is just converted seawater that has seeped way down into the crust of the ocean floor, close to volcanic chambers, gotten heated up, and coming back out, it has exchanged oxygen with the rocks and comes out in a very oxygen-poor mode. But the chemicals that are in solution during that process, partially dissolved from the rocks and partially liberated as gases from the volcano, are very rich in nutrients for certain kinds of microbes. So there is an entire other ecosystem that is not dependent on photosynthesis that operates on our planet and maybe on other planets. Out of that ecosystem, we may find some life forms that can be extremely valuable in terms of pharmacology and drugs and biotech changes. Now, there is another factor, and it consists of you. In addition to those two massive forces which have been dueling with each other for the last 4 billion years, human activities, mostly in the last 200 to 250 years, have actually begun rapidly altering the system and increasing the ocean's vulnerability to stresses and to perturbations. So we need to understand this. And I'm saying it this way because you need to understand that the dominant forces are the sun and internal energy. And layered on top of that are the progressive capability that human beings and their effects, the products of civilization, have on shifting the balance here. So it's something to keep in mind. And I want to emphasize, I'd like you to read that bottom paragraph very carefully. Take the time, read it. To redirect this course requires clear understanding of the organization and function of marine ecosystems. An ecosystem is an incredibly complex balance of many, many competing factors. And when one or two of them shifts, they all shift. Maybe infinitesimally, maybe dramatically. But that's what we have to understand. And in an ecosystem that would be, say, for instance, the Indian River Lagoon, it's a fairly constrained ecosystem. It's long north-south. It's narrow east-west. And it's a complicated system. And it's right at hand. It's right here to study. That's one ecosystem that's very, very important to study, and I believe Harbor Branch is going to put a significant amount of energy into setting up observing stations where they can actually begin to understand how that system works. But that, by contrast, is a tiny, tiny subset of the global ecosystem that we are all part of. And the global ocean is immensely more complicated than the Indian River Lagoon. So those marine ecosystems are going to be the focus of a huge amount of future research in the oceans. Now, I love dipping in and out of poetry here, and William Blake just had a vision. He had a vision of what it was about. And he says, to see the world in a grain of sand, and a heaven in a wild flower, hold infinity in the palm of your hand, and eternity in an hour. Wouldn't it be cool if that were true? It's not. I like poetry, but it's not true. You can't do that. But we will always try. Humans will never cease to try to synthesize, to try to understand, to try to the innate and insatiable curiosity of human beings. If you don't believe me, watch your grandchildren or your children sometime in the years 2, 3, 4, 5. They will do things that they don't even know are dangerous just because eating that bug really is the only way they're going to find out what a bug tastes like. And they're right. It's just you that thinks they're wrong. Anyway, they're all little scientists. In fact, scratch all of us and we are little scientists. Now, to the complexity issue. The complexity issue is a big one. It's a really important one. And I'm going to dim the lights here just a little. Whoops, lights. To try to, and I promise that, Brian, that I will come back on with the lights. But I want you to be able to see all the complexity. This is less than 10% of the complex processes that actually operate in the global ocean. Less than 10%. And remember, I said they don't just stand alone. They all interoperate. Okay, so that's marine ecosystems. The physics, the chemistry, the biology, it's a big deal. And it isn't just the deep, it isn't just this part driven by the sun, which I'm showing here, but the part driven by the internal energy. The internal energy. I'm going to put the lights on so you folks can find your chair. Is that better? I can redo the first 10 minutes easily, so if you want to stay around later, honest to God, I'll talk every one of you into your grave if you stay long enough. So there's an important step here that shows the integration. And again, here's the global ocean that's captured between the deep heat coming off of the planet and plate tectonics and volcanoes and earthquakes and the solar energy on top. And there's the ocean. For 4 billion years, it's absorbed everything that those two energy sources could put out. And at some level, we are the products of that. So we need to understand this system not just because we're curious, but because we're dependent on it. Now, complexity. Here's one variable, sea surface temperature. One variable. Now, remember all the others I showed you, but one variable. And warm colors here are warm water. Cool colors, the blue is cold water. And you're looking at a single year. That's the film loop is cycling. So it's 1 year. And watch it. If you watch, well, let's watch Florida. You know where that is. So that's, let's see, that's summer, winter. Summer, winter. Summer, winter. Okay? That's the cycle that you're looking at. And that's how the ocean changes in terms of sea surface temperature. And the difference could be a couple degrees between the orange and the yellow. But the dynamics of the ocean, if any of you that can see in the equatorial Pacific, it looks like it's coming off of the Galapagos Islands there, right here. But really, it's actually all of these vortices that are being shed as the equatorial countercurrent migrates to the west are part of the complexity of the ocean. And I will tell you that if you can see it at this level, and you go closer and closer and closer, it's equally complicated. It's turbulent. It's a mess. It's almost impossible. And this is only one variable. So I'm trying to drive home to you how complicated the ocean is. We're looking at the sea surface temperature. Many processes are dependent on temperature. Some processes, chemical processes, react faster in warmer waters than colder waters. There's lots of variables. All right, point made. And here, just to bring it home to you, look here off of South America. The currents in the gyre, the South Pacific gyre, the currents are migrating from cold area down here up along the coast toward the equator. Off of Washington and Oregon, the currents are coming from high latitude toward the equator. So this area, although it looks like the reverse of this, there's similarities. They're symmetrically important. And look, let's go back. Here is a cold tongue, a broad cold tongue. And here's another broad cold tongue. See it? And the same is true over here. So the eastern boundary of ocean basins has this broad cold tongue because of that gyre. The western boundary is different. You all know where the Gulf Stream is. That's the western boundary of the North Atlantic. And it has a sharply defined, rapidly moving, much more rapidly moving than this current, rapidly moving current called the Gulf Stream. Look off of Japan. There's a comparable process taking place there. And although it's not as well limbed here, it's the same is true here and here. The eastern boundary currents are broad, the western boundary currents are narrow and focused. So by studying one of these systems very, very well, we learn something about all of them. Remember that. I'll be back to that point. And the complexity goes on. This is a food web. Look at how complicated that is. What happens when you start removing anything? You would think, well, no problem. You just remove it. Take krill out. Well, what does krill support here? And what would collapse if krill disappeared? Everything. I love that. We should go on the road together. There's a lot of complexity that's involved here, and this is just the biology, not the physics or the chemistry, and the way the physics and chemistry and biology prey on one another. Bad term. Okay, now, shifting slightly, although not entirely, about half of the CO2 that has been generated since the Industrial Revolution by burning fossil fuels has actually ended up in the ocean, and that's a good thing. We would be in rough shape if not. And here is the global carbon cycle after the Industrial Revolution, where we're putting out a lot of fossil fuel, where we have strip mined areas, where we have taken chemicals and oil out of reservoirs, burned them. Lots of changes have taken place, but these processes still operate. How do they operate? Gas exchange, for example, between the air and the atmosphere. How does that happen? You have dead, calm sea with a flat surface. You have atmosphere above. You've seen this offshore. And you have water below. How does that work? It can't be very efficient. Well, it's much more efficient during big storms. I mean big storms. The exchange between the atmosphere and the ocean takes place most effectively during big storms, high winds, huge waves, crashing, creating billions of bubbles. And due to a phenomenon known as Langmuir circulation, many of those bubbles are wafted deeper and deeper into the ocean as a result of this circulation pattern set up as winds flow across oceans. Why am I bringing the bubbles up? Well, one, bubbles are really cool, but two, bubbles going down, bubbles full of atmosphere, which is rich in CO2, will lose the CO2 to the adjacent water through the wall of the bubble if there's more CO2 in the bubble than there is in the water. And so after a big storm is a time when the ocean has had a chance to equilibrate chemically, certainly in terms of its gases, with the atmosphere that's nearby. CO2 gets into the ocean most effectively under big storm conditions. And when it gets into the ocean, talking about complexity, just still on the theme of complexity, gets into the ocean, phytoplankton, when the sun angle is high enough, become very productive. They grow like plants everywhere. And they use up the CO2, the carbon that's actually in the ocean. It becomes part of the body parts. And then the phytoplankton will eat the zooplankton, and euphemistically, they will package the phytoplankton into fecal pellets, which they then eject. And the fecal pellets are much larger than individual phytoplankton, which don't sink very rapidly. And the fecal pellets will sink to the seafloor, removing the carbon that was in the atmosphere, that came in through the bubbles, that was operated on by the phytoplankton, eaten by the zooplankton, and dropped as fecal pellets to the seafloor, which removes the carbon from the atmosphere for a long time. That's called the biological pump. So you're beginning to get a sense of some of the complexity, and I'm just skating along the surface here. Now, a local phenomenon that many of you are familiar with, some probably to your own personal disadvantage, are hurricanes, but I would argue that you're less familiar with volcanoes here, but there are similarities. They're highly energetic, episodic, difficult to predict, but repeated events that release huge amounts of energy into the environment. Let's talk about hurricanes. What happens when hurricanes happen? Here's one, a cute little one. Here we are located right here. Can any of you wave? Okay, so you see the little blue pattern behind the hurricane? That's the wake. Hurricanes have wakes. And as the hurricane moves, that wake is a dynamic wake, and it creates a vortex underneath, which pulls cold nutrient waters up into the near surface, and they're rich in nutrients. And then when the sun comes back out later, they are very productive, and they're producing zooplankton, which are then eaten by phytoplankton, which are then eaten by zooplankton, which then work their way to the seafloor. So in this sense, you can think of hurricanes as scrubbing the ocean and the atmosphere, in a sense, to remove carbon to the seafloor. It's a very important thing that you may not have seen in your local newspapers. Well, and you say, okay, John, that's great. I'm really delighted to hear that, but we get one hurricane a year here. Big deal. Okay, here's the North Atlantic. And here comes the pattern of the last 25 years worth of hurricanes. It happens a lot. It's a big deal. It's one of the ways the planet manages itself. And when it becomes more intense, it operates more intensely. So it's not all bad. If your home is wiped out next year in a hurricane, just think of the zooplankton and hope that they are not suffering from blockages in their intestinal tracts. I bet none of you will think about that. I hope none of you will. So setting aside the humor, there is an urgency to this issue of how dependent we are on the oceans. And I'll come to that in just I'll come to what the dependency is. But here I want to talk just briefly to those of you that think about such things. There's about 1 billion people out of the 7 billion on the planet that actually are seriously undernourished. And about a third of those actually go to bed at night starving. So there are some very serious issues. And I'm not here with a social program in mind. I am simply saying that unless and until we can manage the life support system on the planet so that all the people that are on the planet now are well cared for, or at least aren't starving, unless and until we can understand how the ocean works, we're going to have a hard time doing that with any sustainable manner. And here is what the population looks like in terms of estimates of the future. So we're at 2011, which is right about in here, which is about 7 billion, right about there. But 40 years from now, there's going to be another 2 billion people plus on the planet. 2 billion. And where are they going to go? It won't be Beverly Hills. And it isn't going to be Westchester County. And it may not even be Chicago. They're going to wind up in the places that are least able to feed them. So when does the planet's carrying capacity become saturated, and what are the consequences? And do we think about that as a society, as a global society? Those are questions for all of you to be thinking about and talking about with your kids. Because many of us will have gone to our reward before this becomes extreme. Let's hope that they have a better reward than ours. So why am I bringing this up? Okay, here is something another thing for you to think about. And this is a little complicated, so give me a moment or two. Here is a timeline. We're starting in 1982 and it cycles to 1998 and then it starts back at 1982. So it's a cycling video clip. This is sea surface temperature. Remember I showed you that earlier with very high resolution graphics that broke out individual events. It was the pixel size in that previous flow diagram that showed sea surface temperature was about 8 kilometers on the side. This is 350 kilometers on the side. So this looks fuzzier. Blue is cold water. Red is warm water, relatively speaking. And so what you see in the equatorial Pacific is periodically there is a strong oscillation between warm and cold, and that's the El Niño-La Niña cycle. That's what it looks like. On the continents, you have bright green, which is growth of vegetation, and you have olive green or brown, which is the dieback of vegetation. Okay, so you have the picture. You're looking at the planet now. Now every one of you is this sort of a budding ecologist, a planetary ecologist. Think of this as your garden. So why am I bringing this to your attention? I sound like I'm pounding on it. Well, if you look carefully at your favorite continent and out of the corner of your eye, you watch the El Niño-La Niña cycle, you'll see that the patterns of vegetation growth shift depending on what's going on in the oceans. And the best example I can offer to you immediately is to look at the Horn of Africa here, or here, it's the same. And notice when it turns green, when it turns bright green, there's enough food there to feed everybody who lives there, plus they can export a little, make a little money. But it's a pretty grim place most of the time. And what goes on in the Central Pacific when the Horn of Africa turns green? It's an El Niño-La Niña cycle. Half a planet away, there's an event taking place here that affects the people over here. That's my point. All of us, in one form or another, are quite dependent on the dynamics of the planet ocean, of the planetary ocean, and most of us don't know it. We simply accept the cycles that we are given. We don't think about it. We don't think about even trying to modify it. I'm not so sure we want to think about modifying it now, but there is a correlation. If we ever did learn to manage the ocean, maybe we could begin to manage the productivity of food growth on the continents. It's just a thought. I put it in your head for discussion with your children and grandchildren. Let me shift gears briefly here. We've been talking mostly about the water and the atmosphere and things of that sort. That's part of the global ocean. But another part of the global ocean is the global ocean basin. And you're looking at the global ocean basin here. You can see where the continents are. But this is a really interesting pattern. This zone, this rich, warm, red-orange zone, are the youngest rocks on the planet. In some places, somewhere along there, that thing's erupting all the time. And you'll notice Iceland is nearby. It erupts a lot. The Azores is right in here. There's other little volcanoes scattered down here, Crison da Cunha and places like that. But this is a very, very vigorous seafloor feature. It's 70,000 kilometers long, and it's a big, long volcano. And one way or another, it's always active. It's always active in terms of hydrothermal activity, geothermal activity, hot water jetting out of the seafloor at 300, 400 degrees centigrade, driven by the heat below. And there's eruptions, lava coming out at 1200 degrees centigrade, 2200 degrees Fahrenheit. This is hot stuff, comes into the overlying ocean. And it's been doing this for 4 billion years. This is a major, major planetary process, and it's out of sight, out of mind. Kind of. Now, how do you study this? Well, let me do an experiment for you, a visual experiment, and again, I'm going to just briefly dim the lights for a moment. And watch very carefully, because I'm going to switch the seafloor on you until it shows tectonic plates. Those are the plates that are the thin plates are only about 40 to 100 kilometers thick that are all over the planet. And the continents are embedded in these plates, just like a big log is embedded in a much thicker plate of ice. Watch. Here it goes, slowly. So now look at the pattern of tectonic plates. It's actually, they're not really colored that. I did that one by accident. Or I did that to bring it out. But let's go back for a moment. And I'll do it again. And you'll notice that the edge of the plates correspond to this hot zone. And so this fundamental process that actually pushes the continents around creates volcanoes and metal deposits and big earthquakes and all sorts of other processes on the planet is directly related to the dynamics of a tectonic plate. And so we were looking, about 15 years ago, we started looking for a place that we could study a tectonic plate. You know, here's a nice one. Not so easy to get to, so we decided, okay, we won't do that. Here's one, but it's just off of places that are restless politically. And it too is a long way away. Oh, look. There's one right off of Washington and Oregon, not far from the University of Washington, where extraordinarily intelligent people work. And it is constantly moving. It's creating earthquakes and volcanoes right here in continental United States. And if we were to study that thoroughly and do it in a new and different way, everybody could be part of it. That's what we thought. Now, I'm going to step back for a moment, and I want to share this with you just because it's cool. You see here, this little ball moving along. That's 1975, 1980, 1985, 90, 95, 200, 205, 210. So right over there, when the ball gets there, watch Chile. 2010 is when Chile, the big earthquake there took place. And you can see this one. See that over here? Watch Chile. Boom. All right. Now, there's another thing I want to, think about this, because you have already become sort of planetary ecologists. I want you to become seasoned seismologists by the time you leave. Watch closely the pattern of eruption, or earthquakes. The locations of the earthquakes are represented by the balls, but when the event takes place, the ball momentarily expands. Okay, so we're going to finish this cycle, but watch. When it ends and goes back here, tell me if the pattern is the same in terms of frequency. You've all lived through this. 1970. I'll bet there's not 10 people in the audience that were born after 1970. So you've all lived through this. Do you see a difference? Bigger, that's true. And boom. Okay. So the person in the back there is programmed to say, maybe that's not this lecture, but the person in the back there is programmed to say, well, John, back in those days, 1970, we didn't know how to measure volcanoes. That's not, or earthquakes. That's not true. This magnitude 6 earthquakes are the smallest earthquakes on here. And long before 1970, we were able to detect nuclear test ban treaty violations in the 60s, actually late 50s, but we didn't admit it. So it's not a matter of lack of data. What you're seeing is a pattern of some sort, and that's the beginning of science. We share this with kids, and we don't give them the answer. We say, kids, what do you see? And they'll mess around with it a while. And then they'll say, I think the last 10 or 15 years of earthquakes have been, there's been more of them and they're bigger. And some of the others will say, well, yeah. And then you wait. You don't get in and say, okay, now here's why. You say, well, how would you study this? What would you do to study more of this? And let them figure it out. This is the kind of education that we can bring if we bring real-time information into the classrooms and we have the teachers who are comfortable not knowing all the answers but knowing how to guide people to answers. Then kids begin to get a flavor of the excitement of science, of why scientists so frequently will work 70, 80, 90 hours a week for not very much money just because we have the potential to see something or recognize something or publish something that nobody's ever seen before. That's incredible. That's incredible. So think about how our education system works and the kinds of things that we can do. Thank you. The kinds of things we can do. And let me take you on another little journey. You've never been underwater by 700 meters, yes? Is that true? Most people here? A couple. You? You've been? Oh, you were just scratching your forehead. I did that once at 200 meters. And I breathed oxygen. So here's the West Mata volcano. Right here in the Tonga Trench, right in that area. Watch what it looks like. This is one of the few times that anybody has ever captured an erupting underwater volcano. And imagine sharing this with your kids. I can't tell if that's coming through. Can you hear that? Yeah. Yes? No? No. Yeah. Yes. This is where people think life may have originated on the planet, in this cauldron or crucible of life. And this is maybe the first time that you have seen an erupting underwater volcano, and maybe the first time you've heard it. Believe me, it won't be the last. This will become more and more and more common. What can we do with things like this to teach? What can we do with things like this to do research, to find out where the next generation of pharmaceuticals will come from? These are the kinds of questions that we pose to ourselves. So submarine volcanoes are really cool things. They're incredibly cool. And I won't read these bullet points to you, but I'll emphasize one or two. About 2/3 of the planet is continuously recreated at ridge crests every 200 million years. There are 5 of those every billion years. And there are 4 billion years, at least. So there are 20 cycles of seafloor that have formed and disappeared. In fact, it's more than that, because there weren't so many the continents weren't as big before. So this is a big process on this planet, and it has created the continents. This process we're talking about, where the seafloor disappears, it doesn't just fully disappear, it plunges beneath North America or South America, creating the Andes and the volcanoes, which creates more of a continent and more ore deposits. So this whole process is related to producing copper, lead, zinc, gold, silver, rare earths, all sorts of things that we use in industrial processes are related to this process. And these are things, one, we don't understand very well, and two, we have not yet learned to fully harness. What we have learned to do is find the residuum on the continents, and we have learned to how do I say this delicately? Lay waste to the countryside while we recover the copper. If you've ever seen a dead copper mine in Arizona, you'll know exactly what I mean. All right, lots of stuff to say here, but let's talk about this plate, the Juan de Fuca tectonic plate, the North American plate, which is right, the boundary is right here, and the Pacific plate. So this plate is moving this direction, this plate is moving in that direction, and this one is moving in this direction. So this one is caught between. It's kind of like the bologna in a sandwich, if you like, and it's being subducted, unlike bologna. It's subducted under North America, and it creates, there's a cross-section through the same area, and here's what the cross-section looks like. Molten rock comes up right here, 2200 degrees centigrade. It cools and forms this tectonic plate, which is this plate here. And then when it gets over here, it plunges beneath North America, partially melts again, and it produces the Cascade volcanoes. It produces Mount Rainier, Mount St. Helens, Mount Shasta, all of the volcanoes. So this process of plate tectonics actually generates more and more and more continental crust, which is what we live on. Okay, now let's look at this environment here just to show you how cool it is. This is a close-up of that area, right where the hot rock was coming up. And the hot rock comes up and only about 5 to 10% of it melts and becomes molten rock. And when it's molten rock, it's less dense than the surrounding rock, so it begins to move up faster. And it collects here under a brittle carapace called the oceanic crust into a tiny little puddle, which is only about 2-3 kilometers across and maybe a ½ kilometer thick. And then the crust above it is very brittle and has cracks and pores and is just very permeable. So there's cold seawater soaking down all through all this. But the cold seawater in the vicinity of this isn't cold very long. It gets heated and it begins to rise like a hot air balloon. And as it rises, the water, the cold seawater comes down, blue comes down, and then gets heated up and rises here because it's heated by this molten rock. And that creates an outflow on the sea floor of 350 degrees centigrade. And it's about a pH of 1.5, meaning it's the acidity of concentrated nitric acid, except that it's 350 degrees centigrade. You put stainless steel into it, and you can sit and watch it curl up as if you're burning a piece of paper. It's bad news stuff, and that is going on all the time. It has been going on as far back in geologic history as we can project. And here's what it looks like when it comes to the surface, because when it comes to the surface, this is the hot fluid coming out. It's full of metals. It's dissolved every rock it came in touch with. It's full of metals, and the metals are super saturated, meaning that the minute this stuff hits the cold seawater, which is all the dark stuff, it precipitates the metals, and it precipitates the metals. So this is a little nozzle. In the time we were watching this nozzle, it grew. It grew. Same over here. And all these have grown from the same process. This is not quite stalagmite, stalactite. This is stalagmite on steroids. It's growing, 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 growing. And this thing will grow in, say, 50 years. It's 24 meters high, almost 75 feet high. And then when there's an earthquake, it becomes unstable, and these things will fall down. So down around the base here is a whole bunch of these, looks like dead trees, but they're copper, lead, zinc, gold, silver, sulfides that have fallen down as a result of the earthquake activity, which opens up the cracks, which causes more hot water to come up from below. It's an ecosystem because everything that you see on the surface are animals. Let's look at one of the animals, what they look like. These are some of the animals that live on the surface. This is a high-definition video of what's known as a tube worm, a pogonophoran. And this is a gill structure that pumps the warm, not really hot, but the warm fluid heated by the volcano inside down into a body cavity, which is not like a stomach really. The whole interior of this thing is made up of a body cavity called a trophosome. And on the walls of the trophosome, there are microbes that live there, and they make a living from the hot water that the tube worm pumps down to them. And they grow and they grow and they grow. And when the tube worm gets hungry, it doesn't actually eat. It just ingests some of the microbes that become part of the tube worm. Symbiotic relationship. We didn't know about it 35 years ago. Just discovered it. They live off of the formation of a metal deposit. It's kind of cool. This part from here to here is about as big around as my thumb. And this is Filamentous Bacteria. These are sulfur oxidizing bacteria here. This is actually a plume. And then there are predators that move around trying to bite these things and nibble them. Tomorrow in my talk at 3:30, I think I'm talking about volcanoes, I have a picture of a predator that comes up and eats one of those things. No, there's never been a study of what they taste like. They have they have kind of a flavor of hydrogen sulfide. There was another question?
What temperature is it there?
Right there is about 17 to 22 degrees centigrade. This is off to the side of those concentrated jets of black, we call them black smokers. They are the 350 degree fluids. When they get to the surface, they precipitate tiny microscopic crystals of iron pyrite, fool's gold, and it looks like black smoke, but it's really hundreds of millions of little particles. I'll show those will be part of tomorrow's talk as well. Now, another really interesting ecosystem driven by plate tectonics, something that you may not have thought about too much before. That wasn't a joke. Incoming turbidites. What does this mean? Well, where we are now is right here. This is where the plate is coming this way and it plunges beneath the continent. So the continent is sitting there like a giant snowplow, if you like, and the sediments that are on the surface here are being scraped off of the plate, and they accumulate here. That's part of the beginning of forming the continent. Just the beginning, and then the volcanic activity here is another part. But what you're seeing above me here is this area. So the flat-lying sediments that are coming in are these. They're called turbidites. The sediments are loaded with fluid and carbon, and so as they get compressed and compacted, the fluid flows out along fault zones, fractures. And when it comes to the surface, it precipitates as something called methane hydrate. This is some of the material. Maybe you saw the drill rig that they tried to plug in the Gulf. They were having trouble with methane hydrates that were precipitating and causing them not to be able to close the thing off. These methane hydrates will precipitate. And I'll show you what one looks like. It looks like ice. If you hold it in your hand, you can light it. It feels cold. You can light it because it's constantly vaporizing and liberating methane, which is basically swamp gas. So it's kind of cool in a classroom, but you can't hold them for very long because at 1 atmosphere pressure and room temperature, that thing will be gone in about 5 hours. But there's a lot of it, and most countries around the world are looking at gas hydrates as a possible source of relatively clean burning fuel, meaning all it does is liberate CO2. The methane oxidizes.
What do you mean the byproduct is CO2, which creates more problem in the atmosphere?
Well, it does, but it doesn't release a lot of the things that coal produces, put it that way. You're absolutely right. Anything you burn that liberates CO2 is a problem, but you know, there are people who say, well, you can't see CO2, you can't taste it, you can't smell it, therefore it can't really be bad for us. I didn't want to get into that, but thank you very much for helping. If you would like to go with me to my next lecture, I'm more... All right, so this is the way we used to do oceanography. I sort of missed the key here. But oceanography has come a very long way since this time. I want you to understand this, that technology has gotten better and better. And, you know, we had troubles in those days. Sometimes the oars didn't work. And sometimes the kids forgot to breathe. But, you know, anyways, Curiosity. This is about curiosity. That's what the whole thing is about. It's understanding the world that you're part of. So the National Science Foundation, recognizing that the oceans are complex and they're central to life on the Earth, on the planet, and that they're changing rapidly and not predictably, has launched the Ocean Observatories Initiative called the OOI, and they are putting your tax dollars, that's one of the reasons I'm here, they're putting your tax dollars into a fundamental shift in the way we study the oceans. And that's what I want to share with you, because what we are doing is using funds from citizens who pay taxes. And it's to do cutting-edge research about how the ocean works. Now, those are high-latitude sites, and I won't talk a lot about them, but if you want to talk afterwards, I'm happy to talk with you as long as you like. Those high-latitude sites are overseen primarily by satellites. So the satellite link up in the sky takes the data coming from the mooring. I'll show you what a mooring looks like. And it relays it back to land, and we get a tiny trickle of data. Maybe it's tens of kilobytes per second. But it's information about how those big storms at those high latitudes actually allow heat and chemical mass to exchange between the atmosphere and the ocean. That's the high latitude southern hemisphere, and then there are two high latitude northern hemisphere systems that are the same, looking at the same process. So we can begin to quantify how the atmosphere and the ocean exchange both heat and chemical mass. The Pioneer Array is off the east coast, and it is a more complex system with satellite links and autonomous vehicles called gliders that are moving around in the area. The one that I want to talk to you about, though, is on the west coast there by 46 North, and it's called the Regional Scale Nodes or the Endurance Array. And that's the one that has a fiber optic cable, undersea fiber optic cable attached to it. Before I go there, the vision of this entire system is to launch an era of scientific discovery and understanding across the ocean basins, utilizing, and the next words are crucial, widely accessible, interactive telepresence. Now, what do I mean by that? Widely accessible means that everything we do is going to be hardwired to the internet. That means you as citizens will be able to watch whatever we are doing and whatever the data is that we are collecting 24/7, 365, it'll be on a website that you can get to. Whether it's high-definition video of an underwater volcano or tracking blue whales or big earthquakes or little earthquakes or migrating marine mammals or big landslides or whatever it is, you'll be able to track it. And we will have visualization capabilities that will allow you to see what's actually happening in your oceans. That's widely accessible. Interactive means that some of the scientists that will be involved in the program will have the ability and the connectivity and the power and the bandwidth to actually reconfigure the robots and the sensor packages that are offshore under control. And when something happens that we didn't expect, we will be able to reconfigure them so that they can track whatever's going on. They can chase the event. And they can measure it. And finally, telepresence means humans will be in the loop, but they're not in the water. Okay? Widely accessible, interactive telepresence. This is a new way of doing science. For the first time ever, human beings of all sorts, scientists, educators, the public, policymakers, kids, whatever, will be able to be there without being there. Literally. Figuratively. Okay, the core sensors, there's over 800 sensors that we're starting with, and there's 49 different types. And they'll be measuring physical, biological, chemical, and geological parameters, which means just variables. And the ones that are at high latitudes, this one, and then the East Coast one, and these two are like this and this. This one is like this. It's fiber optic cable off the coast, and I'll show you that in higher resolution. But I want to emphasize that only this one with the cable will have the very, very high bandwidth. We'll have 10 kilovolts on the wire, this wire, and we'll have 10 gigabit per second bandwidth, minimum. Whereas over here we have 50 watts and the transmission rate of about 10 kilobytes per second. So very different, very important. It would be hard to, we couldn't afford to lay cable all the way to the high latitudes. So we're doing what we can where we can with new technologies in both cases. I happen to be the chief scientist and principal investigator for the one that's off the coast on the Juan de Fuca tectonic plate. That's my job, to make sure that that not only works, but that it's accessible to you. It's very, very important when this comes online in 2014, September-ish, that people know they can get to it and that we can be responsive to what people are interested in seeing. That's our job. This is what a cable looks like. It's really pretty remarkable. This is an incredible technology developed outside of oceanography, but being used inside oceanography. Each one of these fibers, in this case, there's more than 8, but it says 8 fiber pairs. The signal can be amplified, must be amplified about every 50 to 60 kilometers. This is now about 70 to 80 kilometers. Has to be amplified, so we need a big wad of electronics on the cable, otherwise the signal begins to degrade. And each pair of fibers can have 110 gigabit per second wavelengths. That's astonishing. That's astonishing. And it can be powered at basically constant current. So it has a seawater return. I'm getting into the engineering, but anyway, it's a really kind of amazing technology. And this is what it looks like at the planet scale. In 2008, the distribution of fiber on the planet was dominantly of the type that allows humans to communicate with humans. So all the communications you have with anybody and anywhere else on the planet, mostly, with a few exceptions, is by fiber, whether it's on other continents or in the United States. Mostly you have fiber communication now. Satellite carries less than 5% of all of our communications. So this is a big change. And the fiber optic cables that are in place 3 years ago, you could add about 10 or 15 to this. It's a growing industry, and it's very powerful. Oceanographers did not have to develop it. All we have to do is adapt it. This is very powerful as well. Off the west coast of North America, these will be the facilities. Every one of the red dots there will be some sort of an observatory. And this one right here is the one that I'm talking about. And this is what we're seeing. Pacific City, this is Portland here and Seattle there. Vancouver is right up in here. And Neptune, Canada has a cable. We started working with them 12 years ago. They said, we'll do the northern third, you guys do the southern third. This is southern two-thirds. And so we have come out of Pacific City, which is not far from Newport, Oregon. The cable goes all the way across the plate to the spreading center, where there's a volcano called axial seamount. You'll see that in a minute. We'll fly into it. And then it goes out and then down and comes back across the subduction zone. That's where the subduction nose is. And right there is a gas hydrate deposit. So all the things I talked about earlier are the things that were going to be present for 25 years. We're simply going to live there electronically, doing anything we want, changing the experiments, watching the results, covering. When we make mistakes, we have to go out and recover, and we are not going to be hiding. When we make mistakes, everybody's going to know it. It's a choice we've made. We aren't going to go into the laboratory and have science by press conference when we finally discover something. This is your system. You've paid for it. We're going to do it publicly. And God help us if we make too many mistakes. I'm dead serious. Working in the ocean is I mean, many of you live close to the ocean. You know there are times when you're not in charge. All right, but this is the key. The abundant power and the unprecedented bandwidth will allow us to actually operate offshore without being there. I'm not going to beat this one to death, but if you read, let your eye run down the list of items there, significant impacts of decadal oscillations. That's fundamental changes geared to El Nino and La Nina events. We saw some of that. Major weather patterns in North America mostly come across the west coast and then migrate across the continent. They change as they go, but They're well formed when they come ashore, believe me, I live there. Ocean acidification, so it's a big deal. We'll talk about that in a minute. And then the intense oxygen depletion has become a plague for fishermen. It turns out there, for reasons we don't quite understand, there are parts of the ocean that simply run out of oxygen and the fish die. And then there's a lot of ecosystem dynamics. Here is a quick synthesis of the kinds of science that we will be doing. And I emphasize this to you not because you are liable to be one of the scientists out there, although you would be welcome if you decided to go to grad school and or become part of the system one way or another. We are encouraging people to become citizen scientists associated with it. But because climate change studying the ocean, acidification, ocean, dissolved oxygen, ocean, meaning the water, carbon cycle, the ocean, and coastal upwelling, the ocean, all of those are normally done from a ship, and mostly when the ship goes out, it studies this. And then another one, the scientist will come home, change ships, another scientist will go out and study this. And then another scientist will go out and study this. And they go to different places to study those things on different cruises. Same ship sometimes, not always. Same thing here, subduction zones, big earthquakes, spreading centers, the stuff I was just talking about, bathymetric forcing, rough topography, seismic activity, and gas hydrates. All different things to study. All have different kinds of scientists studying them. All go out separately. With this new system, with this cable, all those scientists will be able to study all those processes, all within a large enough volume so that there are representative processes. And that is the way we're going to try to overcome the complexity. I mentioned that there's so many complexities that we, in 100 years, if we kept going out, individual groups going out and study their process, we can never knit it together. But by doing this together on the same infrastructure, and this is the first of them, there'll be 20 of these around the world in 20 years, we begin to get all the data archived, ready for the modelers to deal with. And so suddenly, we're dealing with the complexity. So this is not just a major technological change, but we're entering a new intellectual field. It's very, very exciting. So for those of you, again, I suspect there's a few engineers in the audience. These are the specifics. I won't beat on it very much, but all the data comes ashore in a redundant path, this way and this way. If one of those fails, it still gets to Portland. When it gets to Portland, it goes to Internet 2 and or the National Lambda Rail, which is a much higher bandwidth cable. This cable runs into Canada and then across to Chicago. This one comes down to San Diego and then across and up into the eastern United States. So all of this will be linked to the distribution systems that you all use, which are your email capability. Highly expandable, that's the other thing. I won't beat this to death, but simply show this to you because these are the RSN, the regional scale nodes is what this is called. These are the elements. There are 2 cables, 1 landing station, 1 cable station, 2 scientific sites, this one out here and this one over here, and there are 7 primary nodes, which are these orange boxes. The orange boxes are effectively substations for both power and electrical and for bandwidth. This thing is a mooring that is a next generation mooring. We control this from land, and this thing goes up and down and up and down and up and down and does exactly what we tell it, and it collects data from about 20 different sensors, which is constantly sent back to us. So we can basically drive this around, up and down. This one is over here, and it migrates to the bottom and then back to the top and then down to the bottom, 3,000 meters. Here's a simulation or an animation of what we're talking about. There's the one that goes 3,000 meters. See, it's almost at the top. But this one is the 200-meter one at the top. You're seeing it here, and you're seeing it here. So we see something. We see Calanus pacificus, which is a type of copepod. It's sort of vaguely like a shrimp. And we find there's a layer, and we want to study the layer. So we were able to focus this thing and just go up and down in the layer. We photograph them, we can sample them, we can analyze them, we can look at all sorts of things, how many there are, why they're there, what the chemical conditions are above and below. and what the fish preying on them might be. So suddenly we're there, able to do many, many things simultaneously in both the water column, and then if you look down here, you see on the seafloor there's lots of other instruments. Here is another way of looking at it. Here's axial seamount. This will be my home for the next 10 years. The spreading center is here. 6 centimeters a year is the speed that it comes, this plate moves at 3 centimeters, this one moves at 3 centimeters that way. So the parting, the spreading rate here is 6 centimeters. On top of that is this volcano. There's more magma coming out than the spreading can pull apart. So this volcano is built kind of like Iceland on top of the ridge crest. And on top of the volcano, there's a depression where the magma is down beneath this thing, and the magma goes up and down because it's fed from below, and then sometimes erupts downhill underneath the ground, comes out over here, and then the floor falls down. Or then it rises again and falls down again. It rises and falls down. Okay. We're going to fly into that now using the same animation technique we saw before. And here's that elevator that we saw earlier. That's the platform at 200 degrees or 200 meters. This is seafloor down on the bottom, and that's real topography. We're looking at real, actual topography. These are hydrothermal systems here with those pinnacles. And see that thing in the distance? Keep an eye on that one. There's another one. They're mobile platforms constantly surveilling. And here is a colony of robots and sensors all making measurements simultaneously of earthquakes, deformation, inflation, deflation. See the cable? We're following the cable. Ooh, just missed that one. And then we come into the hydrothermal site where the cameras are on most of the time. And we have a water sampling device, we have a mass spectrometer, we have all sorts of instruments that are actually functioning in real time and under control from land. This is a new way of doing business. This is a new way of doing business. And I like this quote by Marcel Proust because it gives you the insight that sometimes you kind of know more than you think you know. And sometimes the real voyage of discovery is not so much in seeking new landscapes, but in having new eyes, being able to see things somewhat differently because of some new insight that you had. And suddenly you can make connections that you couldn't make before. Or you become aware of something that you didn't know before. For me, the most exciting example that I have to share is that one day, when we lived in Arizona, my wife took me bird hunting, or bird watching. Boy, that was... Anyway, we went bird watching, and from that day forward, I heard birds. Prior to that, I had not heard birds. I just wasn't tuned into it. They were there. Historically, I'm pretty sure they were there. But from that day forward, I could hear them. And I had new ears. It was kind of amazing. And so what we're doing in oceanography is we're creating new ways of seeing, figuratively because we're doing this integration, but literally because we're introducing new technologies. So the Proust's quote works both literally and figuratively. So here is what I offer to those of you that are interested. What does next generation science look like? There are many, many, many emergent technologies that are being developed outside of the world of oceanography. Oceanographers are not putting huge amounts of money into many, many of these new technologies, and I'll show you some in a minute. But if we had a system like a fiber optic cable, which had electronic and high bandwidth capability, we could very rapidly bring many of these tools that are already existent, that have cost billions and billions of dollars to develop, we can bring them into oceanography, and we transform oceanography not by creating from square one these new eyes, but simply by adopting them and putting them in the hands of our young people who are capable of being immensely creative under those circumstances. So here's an example. Start in the upper right. The the robots, the kind of research that's going on in robotics is amazing, and it's being developed by many, many sources. Many sources. Lots of money is going into robots. Some that simulate humans, some that can have artificial intelligence that's unbelievable. All of that could be available on a fiber optic cable somewhere with eyes that you can see down here. New digital imaging technologies, which I would be willing to bet half of you have at least something like this in your pocket. 15 years ago, you had nothing like this in your pocket. And what is it going to be like 15 years from now? Ask your kids, what will this be like? It's probably going to be, it'll be embedded in your head somewhere. There's a bad story about that from Michael Crichton, don't read it. But what I try to get my students to think about is the rate of technological change is changing. The speed with which we go into new ways of doing business is getting faster and faster. Meaning that 2 generations of iPhones or mobile platforms from now is liable to be almost unrecognizable by people who 10 years ago maybe had a cell phone that was, as big as my arm. So how do you educate people for that? How do you teach your kids, not that it's happening, because they know that better than we do, but how do you teach them to be critical? How do you teach them to analyze? How do you teach them to check facts? How do you teach them to take pride in creating something new? That's what universities need to be doing at this stage. We need to be not trying to simulate the internet, not trying to create all the new technology, which is in the hands of people that are much better at it than academics are, but to begin to get our intellectual and cultural arms around the rate of change that's taking place, and arm our children and their children with the ability to remain flexible. I mean, everybody should have to be, I guess, an intellectual entrepreneur of some sort in order to take advantage of the next opportunities. And in the ocean, so crucial for us to understand, we're right at this break point, this Moore's Law break point, as we go into an era where the technologies are aligned now in order for us to have all these capabilities. Here, ecogenomics, I'll come back to this. But as a result of the Human Genome Program in the 90s, they predicted it was going to take 30 years to finish the human genome. And they were done 10 years later. Why? Because the rate of change of ability to sequence genes increased so fast that they were done by the turn of the century. Not quite done, but far enough along. And it hasn't stopped. 10 more years, and what's happened? They can sequence genes much faster now than they could 10 years ago with less investment, smaller space. You could have something that's the size of my briefcase over here that could be a laboratory in which you could sequence a gene in an afternoon or maybe even a couple hours. It used to take a room this size with instruments pumping away for 3 months. So the rate of change has an effect, and it's getting cheaper, it's getting smaller, and it's getting faster. That's all to the good. If we need to understand the oceans, we turn to things like this. The digital imaging. It would be useless to us in the ocean if we didn't have fiber optic cables that could bring massive amounts of information home instantaneously, at least at the speed of light. Okay? And we wouldn't be able to digest most of this if we didn't have increasingly complex computers. And if any of you don't know about cloud computing, the truth is you actually do. If you have ever Googled anything, imagine what kind of machine is at the other end of your Google query, where in about 0.2 seconds you have a 500,000 answers. Think about it. We all use the clouds. We don't think about them. That's not going to change. That's going to get better, I think. Nanotechnology is utterly beyond description, and I won't go into too much of it here, except to say that it synthesizes the idea that everything is getting faster and smaller and more effective. There are problems with all these, but none of the routine money spent in oceanography has gone into the development of all these. And power, right now we need the cable with the copper interior to get power out to the seafloor and beyond. 20 years from now, we won't need that. We'll have been smart enough to extract energy from the entire environment. So my argument is, for now, this fiber optic cable system that we have off the coast of Washington, Oregon, is the ideal place to bring all of these things, the next wave, into oceanography to test them, figure out what works best, and then export that to as many places around the country and around the world as we can. In the meantime, I have to tell you that I've been to 14 different countries in the past 4 years. Every single one of them is asking how they can build something like this in their waters. This isn't going away. This isn't going away. And here's my key point of the whole talk. Delivering power and bandwidth into the ocean will dramatically accelerate the rates of technological adaptation. And this one, read that and think of your kids and your grandkids. They will gravitate towards something where they think they can be innovative, where they think they can make a difference, where they can explore a world that nobody's been to, which is the world of the ocean, where hundreds and hundreds of processes are constantly interacting. That's a great challenge. Here's a quick dramatization, I suppose is the best way to put it, of the ecogenomics. Say you have this cable and you have these little tiny laboratories. This one's about the size of a trash can probably in your kitchen. And it's on a cable and it's connected. And you have 4 or 5 of them, maybe 5 or 6. And an event takes place in the area. Say it's a red tide, or say it's an erupting volcano, anything that changes the environment fairly dramatically, and you want to know what happened. Well, the first thing you do is turn on the pump, and you pump the fluid in, and you extract the bacteria and the plankton, and you prepare them for analysis, and you hit the analytical button, and less than a minute later, all the genomic information that you want about who's there and what they're doing to whom comes back to you on the cable. You're not there, you're not within 300 kilometers. But you're getting data that you couldn't believe even a year ago, even 2 years ago. Can't believe it right now. But we're doing on a one-by-one basis, we are now doing these experiments in a much more clumsy size. It's actually about my size. But the rate at which it has been shrinking is a Moore's law function. Look out 5 years. Look out 10. Another one. What we have found is wherever we have watched earthquakes and volcanoes erupting on the seafloor, we have found vast amounts of microbial material come issuing from below the seafloor. When the rocks crack, we say the bugs bloom. Well, the bugs come out, the microbes come out of the seafloor, either because they have been subjected to new flow of fluids, or because the nutrients that come from the volcano feed a bloom in those microbes. They multiply. Well, this is only 2 years worth of earthquakes in the Juan de Fuca area. It's not like we're going to build this thing and nothing's going to happen. Something's going to be going on all the time. And we're only looking at magnitude 3 here. So there are magnitudes 1 and 2, and that's 2 orders of magnitude more earthquakes. All right, so what do? Well, we put in the cable, which has already been laid. That segment is actually there, and that segment is in place as well. These nodes go in this coming summer. We'll be doing this live, so we'll be streaming video. If you want to watch it, watch the website at the end of the talk to tune in to our live video. And now we're simulating the earthquakes. We've measured these earthquakes using other systems, and we know from looking at the earthquake patterns that there's harmonic tremor taking place here, meaning that something is moving through the rock, the cracks. So we send in the troops in the form of autonomous underwater vehicles. One flies right into the erupting plume and has to stabilize itself and has to protect itself, but it samples the hot water coming out from the volcano and the particles and the microbes, and then releases a flotation cylinder to the surface, and we send out an autonomous airplane, like the ones they've been using in Afghanistan for other things, to pick this thing up, and it comes back into a city on the West Coast for analysis less than 24 hours from the time that it issued through the seafloor. This is not far-fetched, it just hasn't been done. This is the kind of thing that we can engage our kids in. I'm fully in favor of exploration of space as long as we include inner space, which we all depend on more than we depend on what's going on in the outer solar system. We do depend on what happens in inner space. I would like to see us continue to explore vigorously. For example, here's the volcano. I showed this to you earlier. Here's a couple instruments that we're going to have there. These autonomous vehicles are constantly patrolling. And there's a closer one here that will be, this is called Sentry, and it will be able to follow that's the caldera there. It'll be able to follow close paths there. And the volcano will eventually erupt. This is a simulation of the eruption. The plume rises, and there's all kinds of stuff in there to be sampled, as well as heat to be measured. And here's an autonomous vehicle moving here. These are the moorings I was telling you about before. But here's one. I don't know if you can see it back there. There's one. See it? It's independent. It's been trained to fly through the plume, measure the temperature, look at the flow rates, take samples, and then eventually jettison them. So we have the ability now, we're right on the threshold of having the ability for the first time ever to look at what this 70,000 kilometer long ridge crest of volcanoes does when it erupts into the overlying ocean. Is it an asset? Is it a liability? Is it both? Is it something we need to understand? Is it just a phenomenon? Do we care? This is what research is about. Taking risk, understanding things we don't understand, and then figuring out how to use them. I'm going to bypass that because I want to get to the questions here as quickly as I can. We will be tracking mammals all over the North Pacific, and you will be able to watch that on your websites. Now, I want to remind you of what happened on 9/7/2001. Everybody remembers 9/11, but on 9/7, some doctors in New York City removed the gallbladder of a woman who was physically in France. Why that woman allowed them to do that, I do not know. But they did it successfully. And if they could do that 10 years ago, imagine the kinds of complex operations we could get involved in the environment, on the seafloor, or in the water, where we're studying natural environments without having to extract everything, bring it back to the laboratory, freeze it, kill it, do all the things they do. We can actually look at things in the natural environment for the first time ever. Here's the system we're talking about. In 5 years, we'll finish the construction. It's got a cyber infrastructure which will collect the data and archive it and make it available to you. It has a coastal global component, and the regional component is the one I've been talking to you about. Then it will transition to 25 to 30 year period as a science program where there'll be marine operations, there'll be computer cyber operations, and there'll be science operations. We have to maintain the thing for all these years. Every year we go out to do something, and every year we will go out with our cameras turning, so you'll be able to be there with us if you want to watch. And we'll be watching things on the seafloor through the cable as well as from the ship above, so you'll have a dual view. There are a number of key ideas. The main one here is that for the foreseeable future, the Northeast Pacific is going to be a laboratory for next generation science with a long-term commitment. Canada and the NSF have committed to putting in excess of $250 million into the construction, and then they've agreed to keep it going for another 25 years. That's the better part of $1 billion. So we're talking about a NASA-scale experiment of taking up a location in a fascinating inner space environment, which is going to involve how the ocean works and how volcanoes work and how whales move and how fish stock migrates and how earthquakes take place. It goes on and on and on. In my view, I think it's comparable to the launching of Sputnik as we learned how to use satellites. We're in the same kind of situation. And I believe that Harbor Branch, particularly with Margaret Line in here, Harbor Branch has a history of working the oceans. The idea of working remotely without having to be there means that they certainly can function in systems that are around here. But because of the internet, they don't have to confine themselves to their own backyard. We can have people from anywhere working on the system that we're talking about because it's as close to you as your computer. Now, I don't want to go away saying everything is simple. I don't want to go away giving the impression that there are no problems. And I will point to academics like myself who are dreamers, who try to get major programs going, and we have in this case. But oceanographers and researchers in general in academic systems tend to be a little competitive with each other. They tend to be trained to be very creative, but publish their own papers. So you like to keep your data to yourself. We're not doing that. All the data is available to everybody. But we need to cooperate. We need to work well together across not just institutions, but across the country, across the world. We all need to work together to understand these oceans. Because if we don't, it's going to be a little bit like herding cats. I mean, you've heard the metaphor, well, you know, geez, it's like, well, getting a bunch of academics to all work smoothly and well together is a challenge. That may even be true of companies, I don't know. But we're all going to have to work together. Federal government, companies, academics, the public. Remember, you guys are much more powerful than you think. Do you remember the Hubble telescope? It was the government that wanted to end it. Do you remember who kept it around for a while?
This man right here is my great-grandfather. He's the first cat herder in our family.
Herding cats. Don't let anybody tell you it's easy.
Anybody can herd cattle. Holding together 10,000 half-wild short hairs, well, that's another thing altogether.
Being a cat herder is probably about the toughest thing I think I've ever done.
I got this one this morning, right here, and if you look at his face, it's just ripped to shreds, you know?
You see the movies, you hear the stories, I'm living a dream. Not everyone can do what we do.
I wouldn't do nothing else.
It ain't an easy job, but when you bring a herd into town and you ain't lost a one of them, ain't a feeling like it in the world.
So think about that. We want to spend your tax dollars wisely, but we may sometimes need your help. We need your help to know what we're doing, to care about what we're doing, to be involved, maybe to have your children become involved. One way or another, insist on getting what you're paying for. For example, this is what a classroom of the future might look like, where every student has a live feed from the sea floor coming into their computer. And before long, you would find that the computers seem to disappear. The kids get so into it. You can see, and they're there. They're there. And then we make another transition. We make this even more available to you by basically putting it in your pocket. This is doable. This is eminently doable. So I'm turning the lights on, sir. Hang on. Ma'am. Okay, so you will have this ability. You will be able to track what's going on. You will be able to do it from your mobile platform or from your, whatever the computer is you use. Or I think the day will come when we will eventually have an equivalent of a scientific CNN. I mean, my God, people watch C-SPAN, right? we ought to be able to match C-SPAN with underwater volcanoes, don't you think? It's just a joke. It's not a joke. Okay, so here is the ultimate goal. Real-time interaction with the ocean from anywhere on Earth. And I want to share with you the words of T.S. Eliot, a poet. T.S. Eliot won the Nobel Prize for Literature in 1948. In 1943, he published the 4 quartets which if you haven't read lately, I urge you to get them out and read them. Some of it's hard to read, I grant you, but there are parts of it that are absolutely fantastic. And one of them has to do with his view of what we're about as human beings, as scientists, as citizens, as children, as poets, whatever. There's a lot less difference between us than we believe. And he said, and I quote, "We shall not cease from exploration, and the end of all our exploring will be to arrive where we started and know the place for the first time. Arrive through the unknown remembered gate, where the last of earth left to discover is that which was the beginning. At the source of the longest river, the voice of a hidden waterfall, not known because not looked for, but heard, half heard in the stillness beneath the waves of the sea." Thank you for your patience. I would love to take questions. If you have some, please just, if there's no point in clapping because that's a waste of time, but if there are some questions, that would really be fun. I mean, one of the reasons we do these things is because it's just fun. Sir?